Now we're going for a hierarchical clustering, which is another approach completely different than k-means. So we close the deal with k-means, that's k-means, period. Now we're talking about hierarchical clustering, which comes from the idea that, you know what, maybe I don't want to determine k. Maybe I just want to try them all. And then after I try them all, I will see what happens. And then I will choose, and then I can choose to have k equals 3 or 4 or 5. Then I can basically just jump between them and decide for myself. So this is the idea behind hierarchical clustering, because the output of hierarchical clustering is actually a dendrogram, such as this thing over here, which basically gives you the results for the clustering of every possible clustering from between having every point in a cluster, which is down here. Every point is in its own cluster, which makes no sense, but still it's how it is. And then as you go up on this dendrogram, in any place that you cut, let's say, so to speak, if you cut the dendrogram in any place in the horizontally, you will end up with a possible partitioning of your data set into a specific number of clusters. So for example, in this case over here, we have 3 clusters, because everything that is, let's say, below this branch here, everything that's below this branch, and everything that's below this branch, they're 3 different clusters. Because I chose to cut it like that, if I cut it over here, for example, then I have 2 clusters. Everything that's below this point, let's say, well, I can actually draw that. So for example, if I were to say, no, I want 2 clusters, then I would cut over here, and then everything below this point, everything below this point and everything below this point will be cluster 1 and cluster 2, for example. All these points over here. There's another example as we go. Yeah. The extremes divide the data into either one cluster on the top. So for example, if I were to cut, I don't know, if there was something like this, and I would cut like this, then everything would be in one cluster. That makes no sense. But in the bottom here, everyone's its own cluster. Wow, that was bad. Yeah. So how do you do that? What's the algorithm behind this thing? There are 2 ways of doing that: bottom up or top down. I'm going to explain to you bottom up or agglomerative algorithm. You can look it up later to see if you to see the other one. But basically, one starts from every point being in its own cluster and then aggregating them, and the other one starts with all points being in one cluster, and then you start cutting the cluster down until you get what you want. But we're going to focus on bottom up. So we start with each element n in its own cluster, and the dendrogram is empty because we don't have clusters, right? So we have, right now we have 9 clusters because we have 9 points, and each point is its own cluster, okay? The next step is we merge the 2 most similar clusters into a new one. So again, as I've said before, every point is in its own cluster. So when I say, so at this point, when I say merge the 2 most similar clusters, I'm actually saying merge the 2 most similar points, simply because each point is its own cluster by now, okay? And then we put them over here at the similarity height. So the similarity between them is, I don't know, something close to 0.5, maybe 0.4. So they end up being over here because of that, because the similarity between these 2 guys is 0.4 in this, you know, in this feature space that we have over here, which is artificial. Next step, well, actually, that's it, to be honest. And as you can see here, now we have actually 8 clusters. We don't have 9 clusters anymore because we have 1, 2, 3, 4, 5, 6, 7 points, which are in their own cluster. And then we have the red cluster, which has 2 points. So now we have 8 clusters. And then if we repeat this process, again, merge the 2 most similar clusters, not points, not necessarily points. They may be points, but they may also not be points, right? Because I have started merging them. So merge the 2 most similar clusters, and it just happens that in the next iteration, the most similar clusters were 6 and 1, which happened to be points, but that doesn't matter. And then they were put over here again slightly below 0.5 because their similarity between them is something like 0.40 something. And then you keep repeating this thing over and over and over. And as you can see now, we have 7 points, 7 clusters, because you have 1, 2, 3, 4, 5 points, which are their own clusters, and then this one's a cluster, and this one's a cluster, and so on. And now you keep going. That's interesting. Now in the third step, the 0.8 was merged with this cluster over here, not with the 0.5, not with the 0.7, but with the cluster, with the red cluster, because 8 is its own cluster and red cluster. And then the algorithm determined that the cluster 8 and the cluster 5, 7 are the most similar between all possible pairwise similarities. And then you just keep going and you keep building the dendrogram as they come. And as you can see, in this case, the 8 is connected to 5 and 7 at the same time because it's a cluster. Yeah, and then you keep going, and then 6, and then the next time you will have 5, and then 4, and then 3, 2, 1, and so on. And you keep going until you have just 1 because everyone's in the same cluster, and that's it. The dendrogram is built. And after you have the dendrogram, you can just cut it anywhere you want, and anywhere you cut, you have a specific number of clusters because we went from 9 to 1 in each step. One thing that you may be thinking about is like, how can I compute the similarity between clusters, right? Because the similarity between points is obvious. It's just the length of the line that connects the 2 points. So if I want the similarity between 2 and 8, I just draw a line here and that's it. But how do you compute the similarity between 8 and this cluster over here? What does it mean to be similar? Well, there are actually many ways to do that. Actually, the 4 main ones are the average, for example. So it's the mean distance between all points from A and B. So in this case, average would be the distance between 8 and, let's say, the centroid of this cluster, because that would be okay, this is what I consider as being the distance between the 2 clusters. It could be single, which is the smallest distance between points from A and B. So in this case, it would be the distance between 8 and 5, because 5 is the closest to 8, between 5 and 7. So it's 8 and 5. This distance would be considered as the cluster distance. It could be complete, as we say, which is the largest distance between points from A and B. So in this case, it would be the distance between 8 and 7. That would be defined as the cluster distance. Or it could be centroid, which is the distance between the cluster centroids. I said a completely wrong thing with the average one, which is the mean distance is not the same thing as the distance between the centroids. I apologize for that. I mean, in this case, the average here would be actually that we would compute the distance between 8 and 5. Then we would separately compute the distance between 8 and 7. And then we would take the average distance between these 2 distances that were computed. And if both clusters had like 10 points each, then you would still have to compute like every pairwise distance between them and then take the average, it can be a little bit problematic. But the centroid distance is a little bit simpler. So it's actually the distance between the cluster's centroids. So then it's what I said, which was that you would take the centroid of one cluster and the centroid of another cluster and then compute the distance. That's problematic. That's not very common for a variety of reasons. So average, complete, and single are the most common, okay? And as you will see, there's an impact of that in the shape of the dendrogram. So if you're curious, this is the full dendrogram for the example that we were looking at. And as you can see, it's very interesting because some distances are more obvious than others, right? So for example, think about this. 2 is in this purple cluster, together with 8, 5, and 7, because that's how the algorithm happened to assign that. But if you think about it, 2 and 1, they are much closer to each other than 2 is close to 8, for example, or even to 9, especially to 9. So to say that, if I were to partition this data into 2 clusters, I say, okay, I want 2 clusters, then 2 and 9 would actually be in the same cluster. But 2 and 1 are much, much closer to each other. So you might expect, like, if you didn't, you know, if you didn't have the clusters, if you just looked at the data, you might expect that 2 and 1 would end up being in the same cluster because they're very, very similar. Actually, they're very similar. They're very, very similar. They're much more similar. 2 is much more similar to 1 than it is to pretty much anything else, right? So so it's weird that they end up being separated, but that's just how the algorithm does, and no algorithm is perfect, right? Yeah, and yeah, so this is what I said before about the cut. So I say a horizontal cut would define the number of clusters. And if I wanted 2 clusters, then basically I do a cut over here, and then everything that's below this point is 1 cluster, and everything that's below this point is another cluster. And that's what we have over here if we decide to use, you know, 2 clusters. Cool. So yeah, and this is interesting. For example, if I actually cut it a little bit below here and I say, okay, I want actually 3 clusters, this is what you would get, which is quite interesting. 9 is so much farther away from everything else that it actually becomes its own cluster, even if you just ask for 3 clusters. And then you get this configuration over here, which is, it's interesting. It's, for some, this may look good. For others, maybe it may look weird. These are the results of using different linkage in the shape of the dendrograms. As you can see, for example, single linkage generates this kind of a weird, let's say, skewed dendrogram, where you have a lot of these points being added into a cluster very late in the process. So up to this point over here, so up to any point over here, you have these small clusters with just individual points, which maybe is not what you want. So average and complete tend to generate more balanced dendrograms. So that's usually, I mean, I would say probably this is recommended to use either average or complete linkage. So you get more balanced dendrograms, so that everywhere, anywhere you cut, well, not anywhere, some points are outliers anyway, but most of the time here, where you cut, you will get this more balanced clusters with more points, and other than having these clusters with like 1,000 points in a cluster, 100 points in the cluster, and then 1 point in the third cluster, which looks kind of weird. I don't know. So, you know, in general, complete and average generate more balanced cluster partitions. So I would say it's recommended. And centroid, unless you have a very good reason to do that, don't, because then you get you can get a weird dendrogram where the branches actually go down before they go up, because sometimes centroid distances later in the process, a distance between 2 centroids is actually smaller than it was for a previous clustering, and then the dendrogram goes down again, and it looks completely strange and weird, and just it's not what you expect from this kind of a hierarchical clustering. So I would say avoid centroid linkage. And these are just alternate visualizations for dendrograms, which I think are nice, because I mean this one is the standard one. That's what you're going to see everywhere. But sometimes if you want to visualize your data in a nicer way, then you can maybe use different ones, which I think are also very, very interesting. And you need different algorithms to draw these things. Some important considerations of clustering in general. What dissimilarity measure should you use? So far, I guess what comes to mind for you guys is Euclidean distance, right? Because it is the most common. It's just not the only one. So depending on characteristics of your data set, you may want to choose different ones that compute the similarity between things in a different way. For example, this is a very interesting example that I have in the picture over here. if you look at observations, so these are three, let's say 3 points, 3 observations, three elements of a data set. And in this case, they are representing some kind of a temporal pattern that goes up and down in whatever, like, I don't know, temperature in a day. So it goes up at noon and goes down during the night. So, for example, and then if you look at, if you use, and then you have 3 points over here, the green, the yellow, and the pink one. And you can see in the green one, the temperature goes up a lot and then goes down again a lot and then goes up again a lot and then goes down again and so on. And the yellow one is actually kind of works the same, but in a less extreme way. So it goes up and then goes down, it goes up and then goes down. But if you look at the green and the yellow, they are more or less aligned, right? They go up together and they go down together. They go up together and they go down together. But they do that in different scales. While if you look at the observation number 3, which is the pink one, it looks random. It kind of goes up and down randomly, and it's not really, you don't see this clear pattern as much as you see with the green and the yellow one. However, if you were to use Euclidean distance here to just compare these things, the yellow and the pink one would be much closer to each other because of the scale, because that's how Euclidean distance works. It just takes the points pairwise and just compares them and say, okay, you know what? Euclidean distance doesn't know anything about patterns. So basically, you know, since the points between the yellow and the pink one, they're much closer to each other, then the distance will be small. And the distance from yellow to green will be very large. So this is just an example of when you have to choose a good distance measure for your data, if you know that your data has different patterns that must be considered. What the similarity? Then I cannot say, because there's so many out there, right? So it depends on each case. And another important thing that you must keep in mind always when you're using unsupervised learning, I mean, actually also with supervised learning, but I guess it's very important with unsupervised learning. I can't say that whether it's more important or not, but it's very important. Should you normalize the features? Because sometimes you have features that are in completely different scales, right? So for example, look at this. These are example of people that went to a mall or a shop and they bought socks and they bought computers. So these are examples of people who bought both socks and computers in the same day, right? So if you see the first graph, that shows how many socks a person has bought and how many computers a person has bought. So obviously, most people just buy one computer at a time, right? So you can see here that every person here bought one computer. But actually, I was wrong. It's not about everyone who bought computers and socks. It's a sample of people who bought computers and socks, and some people just bought socks and not computers. So and then you can see that the people who bought socks, they bought like 8 socks or 10 socks or 12 socks, but those who bought computers, they just bought one computer, right? So the scales here are completely different. And it's the same if you look at the price. So you can't even see the prices here of the socks because they're so small compared to the prices of the computers. So the price of the computers here are around like $2,000, right? Basically everyone just bought the same computer here, so that's why the price is just the same. But then you don't even see the socks over here. And again, this has a connection here with the Euclidean distance, because the Euclidean distance basically will just compare the scales of these things. And you know, if you use an Euclidean distance here without normalizing, then basically the computers here, the feature of how many the prices of the computers would completely dominate over the socks. So the patterns that are present in the socks would completely be wasted, would never impact your model in absolutely any way, because the values here are just too small. So compared with the values of the computers. So one solution is to normalize. In this case here, in this example, this is normalized so that both features have a mean of 1 and a mean of 0 and a standard deviation of 1. And then, as you can see, I mean, of course, they will never be, again, how can you measure whether they're equivalent or not, right? But they're much more equivalent than they were before. So in this case here, you can kind of expect that these two features will more or less have the same weight when you're doing whatever it is that you're doing in your optimization. And then one will not dominate the other so clearly, because in a way they are more or less scaled down to equivalent or at least comparable scales, okay? Even though they're completely different things. So this is something that's very, very important for you to consider whenever you're doing any kind of unsupervised learning, especially in assignment 4. Whatever data set that you use, make sure that your features are always, always, always normalized. I can't really think of any situation where you would not normalize your features, unless you're absolutely sure that the original values of the features are important, and you don't want to mess with that because you have a very strong reason to do that. If not, if you're in doubt, normalize everything, okay? Be aware of the options and think about what your data requires.